Now let's take a look at the large displacement rotation and large deformation formulations. Now again, I'll use the same example. Now this time we will not assume that this z equal to is small. It can be any value. So just remember that this is our z, the crookedness we can say, and that's the deformation w. This is the initial configuration. That's the final configuration. So length is L0 and the area of this truss is A0. So as it deformed, length becomes Ln and the area becomes An. That's the rotation theta. Let's say that this displacement is equal to x and this displacement or this distance is equal to z. Now, the first formulation that we will talk about will be the rotated engineering strain. Here we will be using the engineering strain definition. Let's call it epsilon e, and that will be equal to delta L, length change, divided by the initial length, and we can say that that's equal to Ln minus L0 divided by L0. And in that case, the final length will be equal to Z plus W squared plus X squared. Okay. Now, if we write first variation of the total potential energy functional, I'll have the following. The virtual work is equal to stress multiplied with the variation in the strain, dV0, minus the axial load P multiplied with the variation of the displacement. Let's call this equation 1. I forgot to show the P. Let's show that the P is here. Okay. Now I have to calculate the first variation of the strain. First variation of the strain is equal to Ln divided by the initial length. So variation Z plus W squared plus X squared divided by L0. And if you take the first variation of the square root with respect to W, we will get 2 times Z plus W variation in W divided by 2 times square root Z plus W squared plus X squared times L0. So we know that this is the final length. These twos will cancel each other, and the variation in the strain will be equal to Z plus W divided by final length multiplied by the initial length times the variation in the displacement. Let's call this equation star. Now, inserting star into 1, we get the following. The virtual work is equal to integral stress, let's call stress due to engineering strain, Z plus W divided by ln L0, virtual displacement dV0 minus P times the first variation in displacement. So that's equal to so we get the equilibrium equation from this expression. We can write the following. Stress multiplied by A0, L0 will be the volume, divided by ln L0. We have Z plus W, variation in W, minus P times that W. So these two will cancel, and at the end of the day we will have the following expression. Thus P will be equal to A multiplied with the initial area. I have Z plus W divided by the final length. Let's put a note. Remember that the small deformation shallow truss example uses initial length here. Okay, so according to this formulation we have to use final length, and let's say that this means engineering. So this is the stress compatible with this R strain definition. Okay, now substituting E times engineering strain, and instead of final length let's use whatever the length we have, Z plus W squared plus X squared, and put it in this load deformation equation. At the end of the day we get P as equal to E times initial area Z plus W Z plus W squared plus X squared minus L0 divided by L0 Z plus W squared plus X squared. And the other thing that we didn't do here, when you compare it with the shallow truss expression, we said we didn't use truncated Taylor series expansion. So if you take a look at the differences between the shallow truss formulation and this one, remember that we were saying that the rotation is small, so we say that ln could be equal to L0, so the difference is not that much, and again we ignore the higher order terms in the engineering strain definition. Now here we didn't do that, and we end up with a load deformation curve like this. Now what we usually don't like in terms of computations is these square roots. So we don't want to deal with the square roots here. But when you do a final large this type with these assumptions, you cannot escape from these square roots. So that's one way of describing the load deformation curve. We didn't ignore the we didn't say that initial length is very close to the final length. We didn't use the Taylor series expansion, and this is the expression that we will get. Now I will use 3 more formulation, and then I will compare. So this is our first formulation. As a second case, we will be using the green strain definition and do the formulation accordingly. Now, in our first formulation, we say that the engineering strain is equal to Ln minus L0 divided by L0. So we can write this as follows: epsilon E multiplied by L0 plus 2 times L0 is equal to Ln plus L0. Okay? Now, if we multiply E with Ln plus L0 divided by Ln plus L0, then I'll have the following expression: epsilon E is equal to final length square minus L0 squared L0 Ln plus L0. Okay? Why am I doing all these? Because I didn't like the square roots here. So I'm trying to find a way to get rid of these square roots. Okay, so that's why I'm playing with the numbers and try to increase the degree of the strain definition. Okay? So that will be equal to Ln square minus L0 square divided by L0 square 2 plus epsilon E. Okay, so here I actually insert this expression instead of Ln plus L0. Now here I didn't like this, so we are making an assumption here. So large displacement we will allow, but no large strains. Okay, so we say that if strains are small, engineering strain is small with respect to the initial length, we can ignore it and we can write that our green strain is equal to final length square minus L0 square divided by 2 times L0 squared. Now here this G subscript represents green strain. Okay, now as you see, my strain definition will have the length squares. This means that the length has square roots in it, and if you take the square, you get rid of these square roots. Okay, but of course, in order to do that, I have to assume that I have a small strain. Okay, let's continue. Now for the work expression, I need the first variation. Let's calculate that. The first variation of the green strain is equal to ln divided by L0 square, the variation in the final length, which is equal to ln divided by L0 squared z plus w divided by the final length multiplied by the variation in the displacement. So these final lengths will cancel each other, and at the end of the day the variation in the green strain is equal to z plus w divided by L0 squared and the variation in the displacement. Now, the first variation of the total potential energy functional is equal to stress corresponding to the green strain, variation in the green strain, times dV0, we are using the initial volume, minus P times variation in the displacement. So this stress G is referred as the second Piola-Kirchhoff stress. So we have the green strain multiplied by Z plus W divided by L0 squared, variation in the displacement, integrated over the initial volume, minus P times del W. In that case, 0 will be equal to the green strain multiplied by A0, L0 is the initial volume, Z plus W L0 squared, the variation in the displacement, minus P times the variation in the displacement. Now, if we collect everything, we have P is equal to green strain multiplied by A0 Z plus W divided by L0. So this still will cancel. So for an elastic material, we can say that P is equal to E times A0 Z plus W divided by the initial length, and I have the green strain, so I have Z plus W squared plus X squared minus Z squared minus X squared divided by 2 times L0 squared. So these two will cancel each other, and at the end of the day I obtain the following expression: E times A0 divided by 2 times L0 cubed multiplied by Z plus W 2 times ZW plus W squared. So when you compare this expression with the previous one, as you see, this is only a simpler expression, no square roots, it's just a polynomial, so it's easier to solve, okay? Much simpler than rotated engineering strain. No square roots. Much easier to solve. And formulate. So this is the second expression. Here we assume that the strains are small. Okay, so we allow large displacements and rotations, but in return we don't assume large deformation, we assumed small deformation in the green strain definition. Okay, in the green strain and the rotated engineering strain, we are actually assuming that the strains are small, right? We use the engineering strain delta L divided by the initial length. The green strain assumes it's even smaller. I mean, the strain is smaller when compared with the length, so we ignore some of the terms there. Now let's say that what will happen if the strains are large, okay? So for this purpose, we will look at the rotated log strain. So for large strains, we usually use log strain or truss strain. So we are saying that the strain is equal to change in length divided by the length. And from that expression, we obtain the log strain is equal to, from L0 to Ln, L over L, and this will give me, I'll use log E, final length divided by the initial length. And we will say that the variation in the final length is equal to Z plus W divided by the final length multiplied by the variation in the displacement. Now here I have to make an assumption. So we are saying that at this point, so there's an assumption also, we will assume that there is no volume change. Okay, so with this assumption I can write the first variation, the total potential energy functional, as follows. Stress, the variation in the strain, and I'm integrating with respect to the initial volume again, not the final volume but the initial volume minus P times the virtual displacement. So this expression, virtual work expression, is written with respect to original configuration. So 0 is equal to stress corresponding to the log strain, A0, L0, variation in the divided by the final length minus P times del W. So this will give me sigma L A0 L0 Z plus W divided by Ln squared minus P times del W. Then I have P as equal to log stress A0 Z plus W L0 divided by Ln squared. So inserting sigma L as equal to E times epsilon L, I end up with the following expression. P is equal to E times A0 Z plus W L0 divided by 2 times Z plus W squared plus X squared logarithm E Z plus W squared plus X squared divided by L0 squared. And that's an expression, load deformation curve, for the rotated log strain. Here the only assumption that we make is the area doesn't change as the truss continues to deform. So as a final step, let's consider the volume change as well. So rotated log strain with volume change. So here what we are saying is this. Let's say that that's our member. That's the area. So as it elongates, let's do it this way. As it elongates, it will shrink as well due to the Poisson effect. Okay. So I can say that A plus dA is equal to A times 1 minus Poisson ratio times d epsilon squared. Okay, and I can approximate that expression as follows. That's approximately equal to A times 1 minus 2 times mu d epsilon. Now if I write A0 to AN dA over A, that will be equal to minus 2 times mu d epsilon, and that will give me minus 2 times mu from L0 to Ln epsilon, and that's the log strain, and I can just write it this way, 2 times mu from L0 to Ln dl over L. So if we evaluate these integrals, this is what I will have. Log E AN over A0 will be equal to minus 2 times mu Ln over L0. Okay, and this will give me AN A0 as equal to L0 over Ln to the power 2 times mu. So the final volume of that element will be equal to final volume, final area multiplied with the final length. That's equal to A0 multiplied with the L0 to the power 2 mu divided by Ln to the power 2 mu multiplied with Ln, and this will give me A0 initial length to the power 2 times Poisson ratio divided by the final length 2 times Poisson ratio minus 1. Now what we are going to do is we will express the total potential, or the first variation of total potential energy functional at the final configuration, because now the volume is different. Is equal to stress multiplied with the, let's call it epsilon volume, dVn minus P times del W. So this is equal to, again, stress log, I have An times Ln, del n over Ln minus P times virtual work. So instead of this, we will be using this expression. So that's, that's equal to sigma L times A0 times L0 2 mu divided by Ln 2 mu minus 1 multiplied by Z plus W divided by Ln squared del W minus P times del W. So this is equal to 0, and we say that P will then be equal to sigma L A0 Z plus W L0 2 mu divided by length 2 mu plus 1. Now, instead of stress, if you use elastic modulus times the strain, my final expression will have the following form. P is equal to A times E times A0 Z plus W L0 to the power mu divided by 2 times Z plus W squared plus X squared 1 plus 2 mu divided by 2 multiplied by logarithm E Z plus W squared plus X squared divided by L0 squared. So if we consider large deformation as well as the volume change, that's our load deformation curve. So what we are going to do next is we will take our example problem, the truss example, but this time we will use large deformation case, and we will plot the load deformation curves. Okay, now let's compare the results of the formulations that we did. In that case, we are solving the following problem. So this x is equal to 2500 and z is also equal to 2500, and this is our truss. So we start with 45-degree angle. We apply the force in the vertical direction, and this will move to this point and continues. So we will be analyzing the snap through response with a very large displacements. Remember that in the shallow truss formulation, we were taking the z as equal to 25, okay? And these are the rotated engineering strain. This is the equation that we derive. When we use green strain, we get much simpler equation, the rotated log strain and the rotated log strain with the volume change. So let me take this one and put it in the results page as well, so that we'll remember what the problem is. Now, this is the comparison. So we apply the P, and this is the displacement. So when the displacement is equal to 2500, the P is equal to 0. So we are at this level. So this is that point. And then it will continue and it starts to carry the load, and then it will be under tension and continues to carry the applied load. So when the deformation is small, so we are at this region, so the deformation is, we are somewhere here. All the strain, all the formulation gives us the same result. But after that point, they start to differ. Now, the most flexible formulation is the green strain. Remember that our assumption in the green strain is the strain is smaller when compared with the length of the element. So as the strains increase, it becomes more flexible. In the rotated engineering strain, we were using the engineering strain definition, right? Not the true strain definition. But again, compared with the green strain, since we are using the final length in the formulation, and we didn't simplify the strain definition, we see a stiffer behavior, okay? Now, the most stiff behavior is when we use the true strain and the constant volume. It's here. But actually, this is not the real behavior, because we have very large deformations here, very large deformations, and due to that large deformations, there will be a volume change. So when you consider the volume change, this is what we see. So basically, the most accurate behavior is that black line. But as you increase the assumptions you make in the formulations to simplify it, you get significant difference as the strains become larger. But for the small strain regions, these are the small strain regions, all the strain measures gives us the same result. Now, these formulations are large displacement and rotation formulations, but these two assume small strains, whereas these two assume large strains. And you see in the large strain regions we have significant differences. So depending on the problem what you want to solve, you can have different nonlinear geometric formulations.